So in 9.1 we talked about sequences. Okay, the first thing we need to do is differentiate between a sequence and a series. A sequence is just a list of terms. Okay, it's just a sequence of numbers. Okay, a list of terms. A series, however, is what happens when you start adding those terms together. Okay, and so first we're going to talk about the sequence, or a sequence of partial sums. So a sequence of partial sums just means you're adding some of the terms together. Okay, and so we denote any partial sum with a capital S. Actually, we denote any sum with a capital S. And so when you see S with a subscript of 1 like this, it just means the sum of the first term. Well, that would just be the first term. When you see S with a subscript of 2, that means the sum of the first two terms of the sequence. S with a subscript of 3 means the sum of the first 3, and so on. Okay, and S with the subscript of n would just be the nth partial sum. You know, it's our general term, kind of like our nth term formula for sequences. Okay, if a sequence of partial sums converges, then we would say that the series actually converges. So if these values, these S1, S2, S3, if these values, the sums, actually converge, we say the series converges, and whatever number they converge to, we would call that S. Okay, we would say the series converges to whatever number S that happens to be. Okay, so here's all the technical stuff out of your book. We've got an infinite series. Okay, so infinite series just means it goes on forever. Okay, the nth partial sum, like we just said, if we want the sum of the first 5 terms, we write S with a subscript of 5. That means add the first 5 together. If the sequence of all of these partial sums were to converge, then we said the series over here converges, and the limit of S, whatever that is, would be called the sum of the series. In other words, that's what they converge to. Okay, if the sequence of partial sums diverges, then we say the series diverges. Okay, so the convergence and divergence part is a lot like what we were doing with sequences. Okay, but here's the big difference. Here's what you have to remember. A sequence that converges has its nth term converging to some limit. A series that converges has the sum of its infinite terms converging to some limit. Okay, so let me give you an example. Okay, so this first one up here, this is a sequence. Okay, we've got our formula for the nth term. We can list out the first 5 terms. So for the first term we plug in 1, we get 1/2. Okay, the next term we plug in 2, we get 1/4. Plug in 3, you get 1/2 cubed, 1/8, 1/16, and 1/32. Okay, you can see that as we keep on going, the bottom is getting larger and larger, the top remains 1, and so this sequence does converge. Okay, the values are getting closer and closer to 0, and so we would say that this converges to 0. And we could even do it with, you know, we talked about what happens if we call this thing x, and we think about the limit as x approaches infinity, because that's really what's happening here. The bottom's getting really large, the top stays 1, the whole thing gets close to 0. Okay, so the limit of this sequence and the limit of this function are basically the same thing. Okay, now let's take a look at what happens if we start adding these terms together. Okay, so S with the subscript of 1 just means the sum of the first term. Well, that just is the first term. Okay, S with the subscript of 2 is the second partial sum. That means we're going to add the first 2 terms together. So we're going to add 1/2 plus 1/4. So the second partial sum would be 3/4. Okay, the third partial sum, we add all of the first 3 terms together. So we already know the first 2 add up to 3/4. You add 1/8 to that, that's actually going to be 7/8. Okay, and you're probably starting to see a pattern here. If we add the first 4 numbers together, 1/2 plus 1/4 plus 1/8 plus 1/16, you're going to get 15/16. And if you add the first 5 terms together, you get 31/32. Okay, so here's the difference. This is just a sequence. This is just plugging in the numbers 1, 2, 3, 4, 5, okay, and listing out the terms. Okay, when we have the sigma notation in front of it, it means we're adding these things together. And so we're looking at partial sums. The first partial sum's the first term. Second one, add the first two together, and so on. Okay, so this actually converges also. Okay, in fact, if I want to prove it algebraically, I could come up with a formula for any partial sum. Okay, so look, the first partial sum is 1 over 2. The second partial sum is 3 over 4. The third one is 7 over 8. Okay, so we know that the bottom of our partial sums is the same as it was for the sequence up here. So the denominator is going to be 2 to the n. 2 to the first, 2 squared, 2 cubed. Okay, that came right out of this formula here. We can just copy that over. And then the numerator is just 1 less than the denominator. So the numerator is 2 to the n minus 1. Okay, so if we couldn't figure out what this series is converging to, we could try to do it algebraically. We could try and say, what's the limit of this thing as n approaches infinity? Okay, well, you might be able to tell from the original form of it right here that if you have 2 to the n minus 1 over 2 to the n, the minus 1 ultimately won't matter as n gets larger and larger, and so the top and bottom are getting really, really close together, and it's approaching 1. That's what our limit actually is. Okay, you could split this up if you wanted to. You could write this as 2 to the n over 2 to the n minus 1 over 2 to the n. Okay, and if you do it this way, you end up with the limit as n approaches infinity, okay, well, this first part right here, that's just 1, and then minus 1 over 2 to the infinity, so again, that's 1 over some super huge number, that's going to be 0, and we get the same answer. Okay, so the sequence, the terms of the sequence converge to 0. They're getting smaller and smaller and smaller. But the series converges to 1 because the partial sums, as I start adding these terms together, the partial sums are getting closer and closer to 1. Okay, so you're going to have to really think about the difference between these two because you're accustomed to doing this from what we did in 9.1, and now we're looking, everything from here on out is going to be series only. Okay, so let's take a look at some of these examples here. Okay, if you're not sure what to do, you can always start listing some of these terms out. Okay, so this series is going to be equal to whatever we get when we add 1 plus, oh, guess what, the next term's 1, the one after that, the one after that. Okay, we're just going to keep adding 1 to this forever and ever and ever. Okay, so hopefully you can see if we just keep adding 1 that this thing does not converge, it diverges because the partial sum will be getting larger and larger. Okay, but let's look at it. The first partial sum is just 1. The second partial sum is just 2. The third partial sum would be 3. And so to find any partial sum, it's just the term number. If I want the fifth partial sum, it's just going to be 5. And so now we're saying, okay, well, what's the limit of this thing right here as n approaches infinity? Well, it's just going to get larger and larger and larger. The limit doesn't exist. It approaches infinity. So therefore, we would say that the series diverges. Okay, let's take a look at this one down here. Let's list out a few terms to start with. Okay, if I start with 1, I get 1 over 1 minus 1 over 2. Okay, the next one, I get 1 over 2 minus 1 over 3. Okay, now I plug in 3, I get 1 over 3 minus 1 over 4. Okay, and hopefully you can start to see a pattern here. Okay, so this is a special kind of series. It's called a telescoping series. The reason it's, or the property that makes it a telescoping series is that the last part of this term, which happens to be negative, and the first part of this one, which happens to be positive, okay, equal 0 and cancel each other out. And then the same thing happens, we go over here to the next one, and this negative 1/3 cancels out with this positive 1/3. And so if I tried to find the first partial sum, it would just be 1 minus a half or a half. If I tried to find the second partial sum, okay, these would be the first two terms added together, the halves would cancel out, and it would be 1 minus the third, or 2/3. If I tried to find the third partial sum, which is what I have written out here, there's 1, 2, 3. Now the halves and the thirds both cancel out, and I end up with 1 minus 1/4 and get 3/4. And the fourth partial sum, that minus 1/4 would cancel out with a plus 1/4, and it would end up with 1 minus 1/5, and I'd get 4/5. And so basically all this stuff in the middle cancels out, and the value of your partial sum is only dependent upon the very first part and the very last part. Okay, so let's look at this. If we wanted to find a formula for the partial sums, the first partial sum is 1/2, the second one is 2/3, the third one is 3/4, and so it looks like it's going to be n over n plus 1. The fifth partial sum would be 5 over 6, and so on. Okay, so if we look for the limit of this, the limit of our partial sums, limit of this thing right here, our formula, as n approaches infinity, okay, well, these are the same degree, so it'll just be the ratio of the leading coefficients, which should just be 1. Okay, and if we look at our partial sums, yeah, guess what? Look, these are getting closer and closer to 1. 5 over 6, 6 over 7, 7 over 8, and so on. And it should make sense to you that it's going to get closer and closer to 1, because the first term is 1, and all of these middle ones keep canceling out, and this part at the end is just getting closer and closer to 0. The next one would be minus 1/5, then minus 1/6, minus 1/7, and so on. And so ultimately you're doing 1 minus some really, really small number, so this sum is getting closer and closer to 1. Okay, so this brings us to one of our properties of telescoping series. Okay, a telescoping series will converge if this second part right here, the part that doesn't cancel out, at the end, well, I mean, it cancels out in the middle, but the piece that would be left over at the end, if the limit of this, as n approaches infinity, is any finite number, okay, in other words, it's not d and e, okay, if it's any finite number, then the telescoping series will converge. And not only will it converge, but it will converge to the value of the first part of the first term, this part right here, the b1, minus the limit of the second part. Okay, so the one that we just did, is this the one we just did? It is. Okay, so the first, if I wanted to know if this telescoping series converges, I'd look first for the limit of the second part as n approaches infinity. Okay, so n gets larger and larger, 1 over super huge number, okay, it equals 0. 0 is a finite number, okay, as long as that happens, okay, then this telescoping series will converge. If I want to know what it will converge to, it will be the value of the first part of the first term, which is 1 over 1, minus the limit of whatever the second part converges to. Okay, that's the same answer we got a second ago. Okay, let's try another one of these. Here's another telescoping series. If you need to get a feel for what's going on and make sure it really is a telescoping series, because actually sometimes they look like they're telescoping and they're not, just start listing out some terms. Okay, so we plug in 1, and we get 2 over 2 minus 1, or 1. Okay, minus 2 over 1 plus 1. No, 2 over 2 plus 1. Okay, 2 over 2 plus 1, so we get 2/3. Okay, there's the first term of the series. Okay, then we plug in 2. So now we get 2 over 2 times 2 minus 1, minus 2 over 2 times 2 plus 1. Okay, plus, then we have 2 over 2 times 3 minus 1, minus 2 over 2 times 4 minus 1. Okay, so we can see that this is telescoping. Okay, we'll just double check here. This cancels out with this. Okay, this cancels out with this. Okay, so that's what makes it telescoping. Okay, so if this telescoping series is going to converge, then the limit of this last part, the second part, has to equal some finite number. Okay, so let's try this. 2 over 2n plus 1. Okay, it's the limit of that as n approaches infinity. Okay, so once again, the bottom's getting really large, the top is 2, the limit of this is 0. Okay, 0 is a finite number. That means this series will converge. Okay, so what will it converge to? It will converge to the value of the first part of the first term. Okay, so the sum of the infinite series is the first part of the first term minus the limit of whatever the second part converges to, which is 0. Okay, so the sum of this infinite series is 2, or another way to say that is this infinite series converges to 2. Okay, geometric series. So we already talked about geometric sequences. Okay, so if you recognize a geometric sequence, then we should be able to figure out recognizing geometric series as well. Okay, so the one thing that's different here, well, let's look at the one thing that's the same before we look at the one thing that's different. Okay, the one thing that is the same is a geometric series with r greater than or equal to 1 will diverge, just like a geometric sequence with r greater than or equal to 1 diverges. A geometric series where the absolute value of r is between 0 and 1 will converge. Okay, but in addition to the fact that it converges, we can figure out what it converges to. It will converge to a over 1 minus r. Okay, you need to memorize this formula. Okay, a is the first term. And r is the common ratio. Okay, so just like before. Okay, we'll talk about this tomorrow. Okay, you did the sum of finite geometric series, not infinite ones, but finite ones in Algebra 2, and we can actually use this formula to come up with this one over here. You may have even done infinite geometric series in Algebra 2, I'm not sure. Okay, so let's take a look at this one. We've got, okay, so if you want to list out a few terms, we can start with, okay, by the way, I didn't mention this. Somewhere in your notes it's here. Sometimes these will start with 0 instead of 1. Okay, don't be too terribly concerned about it, but just make sure you check it so you know you're plugging in the correct number first. Okay, so if I plug in 0 for this one, I get 3 over 2 to the 0, which is 3 over 1, which is just 3. If I plug in 1, I get 3 halves. If I plug in 2, I get 3/4, okay, and so on. Okay, so the first term is 3, and the common ratio is 1/2. Multiply by 1/2 each time to get the next term. Okay, another way to write this, n equals 0, okay, to infinity. We could have written this as 3, pull the 3 out in front because it's not to a power, and then 1 over 2 to the n is the same as 1/2 to the n. And then you could recognize that a is 3 and r is 1/2. Okay, so yes, this does converge. Not only does it converge, it converges to a over 1 minus r. So 3 over 1 minus 1/2, or 3 over 1/2, or 6. And so if we started adding these terms together, you'd see that eventually that sum of those values would get closer and closer to 6. Okay, let's try this one. I plug in 0. I get 3 halves to the 0, that's 1. The next one's going to be 3 halves. Multiplied by 3 halves, you get 9/4. Okay, so the first term is 1. The common ratio is 3 halves. Okay, and since the common ratio is greater than 1, this will diverge. Okay, I need you to start getting in the habit right now of when a geometric series diverges, giving the reason that r equals 3 halves and that the absolute value of r is greater than or equal to 1. Okay, if we wanted to give a reason for this one up here, the absolute value of r is less than 1, that's the reason. It's more important right now that we can figure out what it converges to, though. If it diverges, give the reason, though, why. The absolute value of r is greater than or equal to 1. Okay, this is kind of a cool application of geometric ratio and the a over 1 minus r, but it's not too terribly important in terms of the AP exam, so let's skip over that. We can come to that one tomorrow if we need to. Okay, so here's some property of infinite series. This shouldn't be surprising because they are actually the same properties that hold true for derivatives, integrals, and pretty much everything else we've done in calculus. The first one is the constant multiple rule. If you have a constant multiplied by some term over here, you could pull the constant out in front and then figure out whether or not the series converges, and if it does converge to something, you can get that number and then multiply by the constant after the fact. Okay, this is our sum and difference that says we can split those apart if we want to and find the value of s, what it converges to for each part, and then add them or subtract them at the end. We don't really use these too much. Okay, here's one of our first tests for whether or not a series converges or diverges. Okay, we are going to spend the next couple of weeks learning a ton of these tests. I'm going to give you a flow chart of maybe a suggested order to check them in. There are a lot of them, okay, so make sure you don't get behind on learning these because it'll be overwhelming if you do. Okay, so one of the properties of a convergent series is that anytime you have a series that converges, the limit of the nth term will always equal 0 as n approaches infinity. Okay, now the converse of that is not true. It doesn't mean that if this part is true, the series will automatically converge. Okay, that's not true. Okay, the contrapositive, however, which is down here below it, is what's going to be really useful for us. Okay, so if a series converges, the limit of the nth term as n approaches infinity is equal to 0. That means that if the limit of the nth term as n approaches infinity does not equal 0, then the series does not converge. Okay, if it does not converge, that means it diverges. Okay, so our first real test here is called the nth term test, and it's a test for divergence. Okay, so here's what we're saying. We find the limit of the nth term as n approaches infinity, and it doesn't equal 0. It equals some other number, or it doesn't exist, or it approaches infinity, anything else. Okay, and if this is true, it tells us for certain that the series diverges. Okay, we find the limit of the nth term as n approaches infinity, and it does equal 0. It doesn't really tell us squat. Okay, this is inconclusive. Maybe it converges, maybe it diverges, we don't know. All those other tests that I just mentioned that we're going to have to learn, if this doesn't work for us, if the limit of the nth term as n approaches infinity is 0, then we have to go and find another test to figure out whether or not the series diverges or converges. Okay, so it is a test for divergence. If the limit doesn't equal 0, it diverges. That's all it tells us. Okay, so let's look at these. Here's how it works. This is the nth term. Okay, so, and this is the first test you're always going to want to try because it is the easiest one. And if it tells us that the series diverges, then we're in luck and we can just move on. Okay, so we want to find the limit as n approaches infinity of 2 to the n. Okay, 2 to infinity, that's just going to keep getting larger and larger and larger. This limit doesn't exist because it keeps growing without bound, and so therefore, since we get d and e infinity and that does not equal 0, we know automatically that this series is divergent. It diverges. Okay, here's one with factorial. Okay, we're going to do limit as n approaches infinity, n factorial over, now notice that this is not in parentheses, this is 2 times n factorial plus 1. Okay, so this is a lot like a polynomial where they have the same degree. If you think about it, no matter what number I plug in for n, this number and this number, they're going to be the same. Okay, if I do 3 factorial, I'm going to have a 6 here and a 6 here. Okay, so if these are going to be the same number, then whatever the top is, the bottom is going to be 2 times that number plus 1. Okay, well, we've talked about this enough in so many different circumstances that you should realize that eventually this plus 1 won't even matter. That basically the bottom's going to be double whatever the top is, and the limit of this thing as n approaches infinity is going to be 1/2. Okay, in terms of trying to figure out whether this series converges or diverges, if the limit of this nth term equals 1/2, which isn't 0, then that's enough to tell us that this series diverges. Okay, let's take a look at this one. Limit as n approaches infinity of 1 over n. Okay, this is a famous, often used series called the harmonic series. We'll talk about it next week. Okay, so we get n approaches infinity of 1 over n. So we get 1 over infinity. So the limit of this thing is going to be 0. Okay, it doesn't tell us anything. We don't know, based off of this, if that series will diverge or converge. So we'll learn another test next week to figure out whether or not this thing actually converges. Alright, so you guys are down to the exercises. You're going to be using on 10 through 10 through 30, you're going to be using either the nth term test, or it's going to be a geometric series or a telescoping series. And that's how you're going to figure out whether or not this thing converges or diverges. And again, down at the bottom on 62 through 66, you're going to do the same thing. Okay, I wanted to point out, let's look at number 30. Because 30 says use partial fractions, and we haven't done that in a while. Okay, so one of the things you're going to have to do when you encounter some of these infinite series is use partial fraction decomposition to write these in a different way so that maybe you can figure out what's going on. Okay, so if you remember, when we do partial fraction decomposition, we're looking to split this thing into 2 fractions. Okay, so I might set it up as like 1 over n times n plus 2 equals a over n plus b over n plus 2. Okay, and then remember, like, we multiply these together, and so we get 1 equals a times n plus 2 plus b times n. Okay, and then we want to solve for a and b, so we talked about zeroing these out. So if I let n equals -2, that makes the first part over here equal 0. So I end up with 1 equals -2b. So b equals -1/2. Okay, and then to make this part equal 0, I let n equal 0. And I end up with 1 equals 2a. That part's 0. So a is 1/2. Okay, so this would be equivalent to n equals 1 to infinity. Okay, I'm going to split this up. So I've got a over n, so that's 1/2 over n. Well, 1/2 over n is the same as 1 over 2n. Okay, and then I'm going to have -1/2 over n plus 2. Okay, so if it's -1/2 over n plus 2, I'm going to put the minus out here, the 1 up here, the 2 like that, and then n plus 2. That's the same as -1/2 over n plus 2. Okay, now hopefully at this point you can see that this might potentially be a telescoping series. And by the way, that's what most of these are if you have to use partial fraction decomposition. Okay, so let's try to plug in some numbers. If I plug in 1, I get 1/2 minus, let's see, 1 plus 2 is 3, 1/6 here. Okay, that's the first one. Okay, plus, okay, I plug in 2, I get 1/4. Okay, so we're thinking, oh, shoot, this may not be telescoping, but let's keep going because sometimes it still works out. Okay, and then we get minus 1/8. Okay, I'm going to move some of this over here and get this out of the way. Not like that. Okay, maybe I'm not going to move that out of the way. I'll just erase some of this. Okay, so we keep on going, and now I plug in 3, so I get 1/6, and then this will be 1/10. Okay, and let's just go ahead and do one more. You're going to have 1/8 minus 1/12. Okay, so hopefully you can start to see that there are things that cancel out. It's just not consecutive terms. So this 1/6 minus 1/6 right here cancels out with this one. Okay, and this negative 1/8 here cancels out with this 1/8 over here. Okay, so it's this that cancels, and this that cancels with this. Okay, so this 1/6 cancels with this 1/6, 1/8 cancels with 1/8, and everything else from here on out is going to cancel out with something. So I've got the 1/6, the 1/8, okay, this minus 1/10 will cancel out with the next piece over here, all the way down. Okay, so let's see if this thing might converge. Okay, we're still going to look at this second part over here. We need to know what the limit of 1/2 times n plus 2 as n approaches infinity is. Okay, and it's 0, and it's frequently 0, like it's been 0 for every single one we've done so far. Okay, so the limit of this is 0, 1/infinity. So that means that this telescoping series does converge. And now let's figure out what it actually converges to. I don't know that we're being asked that, but let's go ahead and do it for practice. Okay, so that first part is actually going to be this plus this. It's the stuff that didn't cancel out. So 1/2 plus 1/4. So it's the sum will be 3/4 minus the limit of this part over here that did cancel out. And so the sum of this telescoping series, this infinite telescoping series, would be 3/4. Or another way to say it is that this series converges to 3/4. Okay, so you guys have some practice problems here. This is not tomorrow's assignment. This is today's assignment and tonight's homework assignment, and then I have another practice sheet for you tomorrow. Okay, so make sure you get as much of this done as possible. I'll answer a few questions tomorrow, but we also have the speaker tomorrow, so I don't know how much time we're going to have, and we have to move on to the next lesson on Monday. All right, I'll see you guys tomorrow.